Hello, everyone. My name is Chase Douglas. I'm the event coordinator here at Eco Canada. So we're going to start things off with the webinar today with awareness on low carbon technology. I'd like to just take a shout out to our funder and um, our partner on this webinar, the Government of Canada. So thank you very much for the partnership on this. So to kick things off, we'll do our traditional land acknowledgement. Eco Canada and myself would like to recognize today and every day the land we are on. Eco Canada is committed to reconciliation, starts with acknowledging our honor and privilege to work and live within this Indigenous territory. Eco Canada acknowledges the traditional territories and the oral practices of the Indigenous nations. So a little housekeeping for everyone. All participants are muted during the presentation. For any technical issues, please use the question box and select Eco Canada. The webinar will be sent out with everyone with a recording of it within 24 hours, so just keep a look on your inbox for that. And then any questions can be submitted through the chat function question box function. Please hold your questions to the end just to make sure that we get through the presentation accordingly, and then you can ask questions at the very end of the presentation. So a little bit of Eco Canada and who we are. Eco Canada is the steward of the Canadian environmental workforce across all industries. We champion end-to-end career of an environmental professional. We not only train and certify professionals, but we also help identify and address labor market gaps. Our efforts to promote and drive sustainable economic growth to ensure that environmental care and best practices is a priority. So our presenter today is Glenn. Glenn is an emissions management consultant, and I'm going to hand things over to Glenn right now.
Great, thank you very much, Chase, and it's a pleasure to be here today. I will share my screen, my presentation, and then we can get moving forward with the content. So today I'll be discussing low carbon technologies in a general sense, looking at high-level topics and also going into some more detailed areas of interest. In order to cover as much material as possible, I'll be moving quickly, but this presentation is being recorded and bringing touch points of awareness is the goal for the time that we have together here today. Okay, oops, apologies. All right, so getting started, most of the audience has probably seen the images here on this opening slide, or at least some version of this content. There's still a lot of sources of carbon dioxide equivalent gases globally, and the industrial sector was considered to contribute over 35% of these emissions from 2022 data collected. This contribution came, as we can see here in this pie graph, from oil, natural gas, steel, lots of different other types of components. And in this presentation, the agenda today is shown here. I'm going to be going through what could be considered as abatement solutions or pathways for the CO2 equivalent gases with regards to methane emissions, zero carbon fuels, also going into CO2 capture, storage, and there's the utilization section. And then finishing off with a little bit on process optimization and electrification. So when we think of the journey of decarbonization that we're talking about here today, we want to see how much we should focus on all the possible solutions. So some organizations have lumped in different types of solutions into the categories of energy efficiency, renewables such as the solar, the wind, the geothermal, CCS, of course, with the CO2 capture and storage, and also switching fuels. So going from the coal, the diesel, the higher emitting fuels to lower emitting fuels, even such as burning natural gas. There's methanol, there's hydrogen, and these percentages shown below each of these boxes shows the potential contribution of each of these pieces of the puzzle. Now, when we're thinking about building up the resources, building up the understanding, Eco Canada is one of the many public places that we'd see presentations such as the one I'm doing here today. But the bottom of the screen also shows a website link to efforts put together by IOGP. And similar in nature to the topics on the last slide, we can see here discussions on methane emission management within this website, reducing flaring, venting, and fugitives, energy operating efficiencies. And for each of these topics, there's guidelines, guidance, best practices, data sheets. and we should take advantage of the public knowledge from these expert groups that are available to us today. At the same time, from this website, I like this waterfall plot showing the overall original emissions that we might be thinking about when we start our journey. From that point, the methane near zero, minimizing flaring, maximizing the process efficiencies and operational considerations. These are foundational improvements that can start the emission reductions. At that point, to take it further towards the net zero goal, we're looking at the decarbonization pathway options such as electrification, renewables, that carbon capture and storage, as well as our alternative fuels. And then what we're remaining with, we hope we'll be able to get at the achievement points that we want within our organizations or our countries or our governments or within our particular regions. So at this point in time, just to bring the audience into the discussion, I want to throw up a first polling question. So hopefully you'll see that on the screen momentarily. And this polling question is really going to these last two slides with respect to where are your operations, where are your personal considerations within some of these different areas of decarbonization. So I'm not sure if we have visibility on the polling question. But if you do see the question being thrown up, please do give the best answer for yourselves. There it is right now. So again, which topic would best describe your current area of interest? And it's the top area of interest. You probably have more than one interest, and we can already see some good answers coming in. Thank you for the participation. Makes me feel a lot better in a virtual setting to see all the answers coming through. And energy and operating efficiency is definitely getting a lot of touch points. That's something that I like to see because looking at efficiency doesn't always have the capital costs. And if anything else, it might even reduce the operational costs. So you have that quick return of revenue or investments that you get from those types of solutions. We have lower on the methane abatement. We do have a bunch going for electrification, alternative fuels, and about an even amount with the CO2 capture and storage. Right, so really appreciate the voting there today. And again, I like seeing that process efficiency optimization, and we will be wrapping up today's conversation with those two topics, hopefully bringing in some considerations that maybe you haven't seen before, maybe some that can just reinforce what you're doing today. So when it comes to those different topics of decarbonization, when we look at the company that I'm coming from, SLB, formerly Schlumberger, and we look at the global decarbonization projects that we've been involved with over the last couple of years and throughout our history, one of the things that we can definitely tell above the fact that there's a lot of different activities occurring is that there is a more large contribution from specific types of decarbonization depending on the region globally. So in the North American market, we can see there's a lot of carbon capture, utilization, sequestration. In other areas, we can see the low carbon solutions are pushing through emission reduction type projects in some of the other areas. And what really I wanted to say to this talking point is that different global regions have different benefits from looking at different decarbonization solutions. So you can't give kind of that overall blanket of a silver bullet when it comes to what you should do behind decarbonization. But here in Canada, of course, we do have some natural resources, some geology, the different types of labor costs, the utility availability and stuff that will all lead towards what might work better in our region versus others. So for the first topic I want to touch on today was actually one that was shown of least interest to the crowd. So maybe this is a good conversation to bring up and bring awareness towards, which is the methane emissions. So when we think about methane emissions and how much that contributes to the overall CO2 equivalent, we can see here one of the plots pulled from a couple of years ago where we can see the direct scope 1 contributions of just methane towards the overall carbon dioxide footprint. Scope 1, just as a definition, is the direct process emissions. Whenever we're talking Scope 2 within this presentation, that's looking at the utilities such as power consumption that's related to the emissions. And then Scope 3 is a much harder to measure and calculate emission footprint, which is the emissions brought through the suppliers or the generation of the materials required for the solutions. So one of the things right here in this upper pie graph is we can see the methane contribution towards the overall CO2 equivalent footprint is very large. When we break that down further, we can see that at least for onshore methane emission sources, there's the cities, pipelines and stations, gas plants, there's the gathering and boosting stations, as well as the well pads. There's a lot of different sources of the methane, and they come in different types of causes, where it's fugitive, it's planned, safety, blowdowns, etc. And one of the things I also wanted to mention in this opening slide for methane is that oil and gas specifically, so not talking about agriculture, landfill type emissions, but we're talking about the oil and gas sector. Globally, it's typically considered around 30%. When it comes to Alberta, though, because of the large activity in the oil and gas sector, there are some numbers that push it as far as 0.75% of the methane is coming from the oil and gas sector. So again, it shows a good opportunity to reduce and even make some monetization along the way. So thinking about what are we doing here in Canada? What are we doing in Alberta in a region with more activity? This is just some of the things that I collected very easily. So one of the things that I'd mention right away is that there's a lot of different pressures trying to minimize or abate methane within the industry. So we have the corporate commitments, so the companies that are choosing to become low emission type organizations. We have the investor pressure, of course, coming through, loss prevention, so literally just not wanting to lose that natural gas that could be brought to the market for sales. We have certified gas that's coming up more and more around the world globally. And we have the non-government organizations, which do the name and shame these days. They say, look how much you're flaring, look how much you're emitting, and they try and put pressure on the companies. And of course, there's government regulations. When it comes to directives, such as Directive 60, kind of summarized here, we're looking at, can we actually eliminate the flares? Can we eliminate the vents? And we also see ramping up the global pressure. There's already 38 stock exchanges with ESG as a listing rule. On top of that, we also are looking at sustainability reporting standards. So there's one scheduled one at the beginning of 2025. It's currently voluntary, but Canadian regulators are deciding if it will become mandatory. At the same time, there's proposed regulatory framework to try and achieve some of the goals of oil and gas methane specific emissions by 2030. So trying to get into the right mindset of methane and why it's such a large impact on greenhouse gas emissions, one of the things that we can look at is the different multipliers, or how much 1 ton of methane is equivalent as a global warming potential as CO2. And we can see there's a lot of different numbers that span over different years. They also span over different time periods of effect of the methane. So there's the 20-year impact and the 100-year impact, knowing that methane will degrade in the atmosphere as it goes through in time and reduce in the amount of intensity. If we do take the 84 multiplier, which is more of the extreme, we can see an open flare destruction efficiency that we might see in an upstream consideration around 96.5%. Sometimes they're lower down towards the 90, 91, 92%. There are some areas of especially assisted flares that go well beyond the 98%, but a 96.5 is something you might typically see. And then we can think of something like an incinerator that has longer residence time, has better mixing depending on the design itself. It has a refractory material, keeps in the heat, high temperatures, and in this case, we can go towards even ISO certification in some situations of over 99.9%. If we think about the open flare with the methane that is slipping through and going into the atmosphere, and we take the base as 100 units of CO2 equivalent, just going through an open flare with lower efficiency to a higher efficiency incinerator can reduce the emission footprint by half. A lot of the flaring vendors and technology providers globally, we've been talking to a lot of them lately, and they've been finding very innovative and cost-effective ways of improving flare efficiencies. And of course, there are also the companies that are reducing costs and increasing the mobility of the incinerators that they can bring to the field. With that mindset, we also want to say, why focus on methane, especially at the beginning of the journey of decarbonization that a lot of companies are doing? One of the reasons why is when we look at the CO2 equivalent GHG emissions in the upstream, we can see a typical asset. They will change depending on the locations and the equipment within the assets, but you can usually say that there's going to be a large contribution of the combustion type equipment. There's also going to be flaring, fugitive, there's going to be venting and pneumatics. But in the case of combustion, usually what you're looking at, once you've created the power or absorbed the heating sources of the energy, it's going to be a majority of a mixture of CO2, nitrogen, and water. But at the same time, the venting and the flaring may be more difficult to collect with the fugitives. We do have a majority of a methane or hydrocarbon content fluid. In this case, it can point towards good techno-economic opportunities. And this could be found from gas recovery into the sales lines. It could be gas recovery back into the feed, the suction of a compressor pump back to the front end of a facility where it can be processed into sales material. And it could also be converted into a product value, such as heating, power, chemicals, etc. When we think of the journey of measuring and tracking GHG emissions specific to methane, there are specific steps that we usually recommend going towards that journey. So for zero emissions, we first say that you should have a good measurement program. The measurement program would be the top-down type measurements such as satellites, drones, planes. We would also have the closer point sensors, the OGI cameras, things that you might find on the ground. And then we also have the flare monitoring, how much hydrocarbons slip and how much destruction efficiency or combustion efficiency, as well as the volumes are you seeing from each of your flaring points. Those all collected together point towards some of the voluntary programs like OGMP, where they're looking towards tracking those types of emissions. And that's a good starting point to understand what you're dealing with when you start looking at the third step, which is the minimization of these. And in the audience here today that we got from the last polling results, we can see that this minimization or this optimization of your process and your facilities to minimize those emissions, of course, is a step that you should be doing before going into any extra activities, such as monetization of the resulting emissions coming from vents or flares. So once again, if you start looking at how do you monetize some of the vented or flared gas, find your solutions, size your solutions, and deploy your solutions in the field, then you go to the step of minimizing and optimizing your emissions from your facilities. You're going to find that suddenly you've over-designed those solutions. This is typically the steps that you want to go through with your progression. When you look at gas recovery systems within your facilities or in the field, one of the things that you can start looking at is smaller gas volume recovery. The EPA references on recovery systems shown right here for tanks or for separators associated gas at different sites. You can see that there's different types of technologies. Some of them, of course, you can consider just simple compressors for the pressure boost. There also is a lot of interest and potential within adductors or adductor systems. Ejectors and adductors are mostly stationary units. What they do is they use some sort of a motive fluid, whether it's a gas or a liquid at a higher pressure, and it creates a suction as it goes through the unit that sucks in the gas that's to be recovered, boosts its pressure, and pushes it further along within the facility or to some point of value or to market. When we think of these types of systems, one of the things we should be thinking of is it has to be fail-safe. In other words, when these systems go down, as they might and they would, we still need to make sure that we're properly combusting those fluids and not just venting them to the atmosphere, going back to the previous slides of the emission impact when you're not combusting things properly. You also want to make sure when you're going through these recovery systems that you do that third step in the last slide before the fourth, which is optimizing the facility process operations itself. So one of the examples would be reducing the oscillatory behavior in your plant as much as possible. So where do oscillatory behaviors come from? It could be from reboilers, having wide temperature ranges or on-off temperature range systems where they turn on, turn off, turn on, turn off, and then you get kind of slugs of vapor, which could be recovered going through your systems. You also have the initial breathing of tanks when you're first starting to fill them up with more live oil versus the dead oil situations. And whenever possible, if you can reduce the amount of oscillatory behavior, you're going to reduce the amount of sizing that you need for these types of equipment, especially if they don't have good turn down capacity on their own. And a lot of times what we see with something like an adductor or ejector is either parallel stages, or we might even have situations of recycled gas to be able to keep the process fluid side the same, keep the same equipment, but it is going to drop your efficiencies. So again, trying to reduce the oscillatory behavior of your equipment, sometimes just through the control systems themselves, is something that you can do to help the step of gas recovery. When you get to larger solutions and you start looking at a quarter or half million standard cubic feet per day type situations, you do have different options, not only of what you're going to bring as value to the market or to yourselves in your own operation, but also to the different lead times and business opportunities. So in this case, we can look at power generation. A lot of companies I've talked to globally say power is king. If you're otherwise wasting the flared or vented gas, why not run it through a purchased or a rental type solution, generate power at site, potentially even bringing it to the grid, even though there are challenges depending on the size of the project. And typically we're looking at lead times of a couple of months to half a year. When we're looking at a second technology route, mainly purchasing types of equipment that can compress or liquefy the otherwise flared or vented gas, dropping out condensates as well, or the LPG, we can then ship that to a point of use, utilization, or sales to the market. And these types of equipment, usually the lead times are half a year to a year. And again, you typically you're going away from the rental or the leases and going towards purchase. The third technology route that we're looking at is potentially converting it to a synthetic liquid, such as synthesis crude, gasoline, diesel, or even synthetic methanol. These technologies are not as mature as the first two, but there are facilities and technology companies that have been running for years now across the world. They have thousands, tens of thousands of hours of operation. They have very solid design specs at micro levels. Unfortunately, though, when we're getting to this size, the lead times can easily be 1 to 2 years. And the reason why I'm mentioning the lead times in this is when we think of 1 or 2 years of lead time for one solution, we're thinking of where we are here today towards the second half of 2024, and we're thinking of the goals of 2030. We can now start seeing that lead times and the scale up that we require might be an important part of when we need to start some of these efforts. Finally, we also have, without any specific business models or lead times, what the zero carbon fuels can do. The lead times typically will be 1 to 2 years, similar to the synthetic liquids. And these also are probably a variety of different business opportunities, such as purchasing, joint ventures, and also I mentioned here DBOOM, which is design, build, own, operate, and maintain from the vendors themselves. Moving into the market space these days, we also see computing type solutions and some of these top solutions also going into gas purchase agreements. So some of the companies will come in and make an agreement where they will purchase your otherwise flared associated gas off of you. And then they will take not only the gas, but they will also take your emission footprint. But of course, they're also going to take the value to market that they create. So again, a lot of flexibility in these things. But one of the things that we do internally as a company that we always recommend to any company that's moving into this space is that you build a rigorous thermodynamic validation of the different solutions. The vendors, the technology providers will always be saying their solution is an excellent solution for you, what you need today, etc. And a lot of the companies actually come to us and they say, we don't know which one to pick, specifically because their flare or venting opportunities, the volumes, compositions, delivery pressure, that will all make an impact on the techno-economics of these types of solutions. So internally, if we pick one of these types of solutions, we're looking at liquid fuels, so a conversion technology. We will actually build out the technology solution within a thermodynamic environment. We will make sure that that is modeled to multiple points of feed compositions. And then we will also have a better understanding of the emission reduction footprint. Unfortunately, a lot of the computing, a lot of the power generation, you are using what would have otherwise been wasted, flared, vented type gases for emissions. But in the total holistic story, you're still not reducing emissions. You're still putting the CO2 into your field. Some of the other solutions you might say, well, if you create synthetic fuels, you create synthetic methanol, you're going to burn it anyways. It's not always the case. For synthetic methanol, as an example, you might be using it as an antifreeze or an inhibitor, especially up in Canada in the northern regions where things might be getting cold. You could ask yourself, how much are you paying for methanol today? And this would be higher grade methanol from the market. Can you offset that cost by creating synthetic methanol in your field today? So you're even removing the inventory costs. At the same time, some of the synthetic fuel liquids, it can go to lubricants because it's very paraffinitic in nature. This naturally comes from the synthetic process and the catalysts. At the same time, it might be used for feedstock in steam cracking plants, creating ethylene, and then downstream to the the chloride monomer type plants and being turned into recyclable plastic. So again, some of these solutions are leading towards non-combustive and non-emission creating results. And those are the things that you might want to be aware of. The other thing that we want to think about, not only with these types of solutions, but some of the carbon capture micro solutions I'll be talking about soon in the presentation, is that micro scale brings different economic considerations. The equipment, as it gets smaller, it does not typically scale well with economics. So you're going to be paying more per unit of production or feed gas coming in. You also have the disadvantage that the instrumentation and the control systems are also not going to scale down in cost as well as everything else. So you have to take into consideration that some of these solutions have a minimum volume where economics will make sense. You also have to make sure that each of these different technologies doesn't come with a utility consideration that is unreasonable, whether that's the logistics, safety, or the cost. So if something needs a lot of power generation, that power generation is being created by something that's emission heavy, that probably won't be a good solution. If you need a lot of potable water in an area that is water restrictive, again, probably not the best solution, but these rigorous models and these rigorous studies that we complete internally is something that we can use to make sure that we're not picking the wrong solution, and more to the point, that with a holistic integrated solution where we might be generating our own power, might be cleaning our own water, might be removing some of the potentially harmful content in the front end through treatment, we're going to find what we would consider the diamond in the rough. Is there one particular technology up here that can go through the average gas flows, the distance to market, the variable flow patterns of the source gas, and even the delivery source pressure, etc., go through all the parameters that might impact the overall economics and find the solutions that are best to move forward? And this is not just in the short term, but we're also looking at long-term solutions. And some of these will probably become more apparent as we talk about the electrification side of things later on. When we talk about our own solutions that we have deployed in the field, just talking about some of the things that have worked for us, this is a picture here of one of our case studies that we brought out publicly using multi-phase pumps. The idea is quite simplistic, but it is very good on emission reduction, that you're going to be boosting the otherwise locally flared gases to a location where they can be utilized, and therefore creating a zero flaring system within cleanups or some of the well testing considerations. The other thing that I wanted to mention on is within our company, we are now looking at always using low emission valves. And of course, we're also selling this to industry. About 90 5% of our valve portfolio is covered with low emission valves, this is not always as easily done when it's on brownfield applications. But greenfield applications, we're always making sure that these are the valves that we're trying to implement. Of course, you want to make sure that they're also okay in applications of new fuels that are coming through. We also want to make sure that all of these are good for aftermarket services and repairs for low cost. But when we think about low emission valves and where they fit into the emission space, we can think about pneumatic control considerations overall. High bleed pneumatic controllers, we can look at how much emission impact they have versus the low bleed or no bleed type considerations. There is a magnitude of impact already on this type of consideration, but we can take it one step further and also look at air compression considerations. So one of the things that we've also looked at whenever we look at decarbonization is, can we use some of the otherwise pneumatic vented gas? We can use it to combust for energy, compress air, and run air through the system. So we're just venting air. In those situations, the power generation and how that's done can become extremely important. So one of the things that I'd like to mention is a lot of the good solutions that we found in industry globally will use something like a Stirling engine. Stirling engines are very robust. They have good lasting power. And a lot of times I've heard stories of hurricanes going through the US. And when they're looking at power sources that are still showing up on the grid, there's a couple of locations running the pneumatic controls in the facilities in the oil and gas industry, and they are those Stirling engine air compressor solutions. So again, these are some of the considerations to go from the older higher bleed valves, low no bleed valves, and going to air compression. So when we're looking and taking a step back, I'm now done with the methane section, and we want to think about how are we going to abate those GHG emissions for the 2030 goals and the 2050 goals. We're planning, we're doing the measuring, we're acting on those solutions and the data that we've gathered, and we're trying to support it and track it by rigorous digital foundation to make sure that we're doing things and tracking things well. But when we think about the overall GHG emissions I was talking about earlier, we have our piece of the puzzle that's methane, but we have a very large piece that's CO2. For the methane, I've gone through some of those solutions, but now I'd like to shift focus in the presentation and go to what we can look at for CO2 related to post-combustion capture, direct air capture, or even those zero carbon fuels. But before I go to the next section, I'd like to bring up a second polling question. I love the activity and the enthusiasm on the first polling, so I hope that you all have the same for this one. And it's finding a balance between production increase with a commitment to climate change. We all know that this is critical, but what would be the top choice on where you are today? Would it be monetizing all your product, getting that revenue stream? Just worried about eliminating emissions, whether that has cost or not? Or do you want to look at both? Do you want to reduce emissions, but make sure that you're making money at the same time so it can compete internally against more production type situations? So far with the results, I love what I'm seeing. I've seen this poll being taken in many different areas of the world. Being here in Calgary myself and being Calgary based and Canadian based, I'm actually really happy to see these, that everything is either just eliminating your emissions or eliminating your emissions with the awareness of trying to make sure that it makes sense from an economic point of view. So thanks again to all of those who put in the voting poll. And with that mindset moving forward, we're also going to start looking at some of the less economic recovery type situations. Again, methane is seen as one where some of the measurements that we have from airplane type situations, it was $30,000 to run airplanes over pipelines within North America for one of the companies. They found a massive leak that they wouldn't have otherwise found, fixed it, put it back into the pipeline, and the payback period was 5 days. After 5 days, you're looking at all that extra revenue recognition. So there's really good payback. These next topics, a little bit more challenging. So when it comes to zero carbon fuels, one of the things that I keep on mentioning on is the location. So one of the things that you could recognize in Western Canada, it has an excellent potential for blue hydrogen utilization. In this map right here, you can see some larger demand centers in both of these maps when it comes to natural gas prices at the top and shipping costs of the natural gas. And in the bottom, we're looking at renewable prices and shipping costs, so more on the renewable electrification side. So when it comes to the blue hydrogen, we can imagine that cheap natural gas as a feedstock is one of the importance behind having right economics. One of the other things that I can mention is around this area, we also have good underground subsurface storage opportunities. So those two put together, knowing that blue hydrogen comes with the CO2 storage or utilization, but then the green hydrogen side of things with the electrification or electrolysis stacks, we also have an opportunity of low renewable prices in our area. So both of these can make sense. When we think of hydrogen, whether it's green or blue, once we've created it with or without the CCUS that comes with the blue hydrogen, we then want to look at the conversion or the compression or liquefaction to going into storage, the transportation, then we want to reconvert it back to something that we can apply to industry, whether that's power and heat, whether that's the industry itself, or even going to transportation. One of the examples I'll show on that. With this storyline, one of the things that we want to do internally is something very similar that we did to the methane story. We want to start with accurate thermodynamics, go into a flexible workspace where we understand reactive and separative units. We also want to make sure that we see the economic impacts, especially with the major equipment that we're going to be looking at, and of course the metallurgy. Hydrogen, those types of things are going to bring different metallurgical considerations. With the hydrogen-induced cracking, we want to make sure that the metallurgy is also well done and the costs associated are considered. But as an example of looking at the thermodynamics and the type of equipment or the process side of things, we can think about natural gas reforming or electrification to hydrogen. We're going to compress it, store it, and we're going to dispense it to hydrogen vehicles on the road. So one of the things we can ask is how much cooling is needed in the dynamic depressurization. Another one is what natural gas city infrastructure can be used with the hydrogen or reused. But when we think about the overall process side of things, we also want to make sure that we can handle the peak rates. So when we're handling the peak rates, we can think of the storage capacity, we can think of how much dispensers or stations we need within certain regions of population, but then the thermodynamics kick in. I don't want to go through too much thermodynamics because of the time limitation we have today, but one of the things I do want to mention is that hydrogen is known to have an inverse JT or Joule-Thomson effect. So for natural gas, a lot of times when you drop it, not extreme high temperatures, but at high temperatures, you drop the pressure and you chill it or you get that cooling effect. Hydrogen does the opposite. It'll actually increase in temperature. So knowing those types of unique thermodynamic considerations of hydrogen, you now have to look at how much cooling do you need depending on the speed of the dispensing. Also, how much pressure drop are you bringing through the system? So these are the type of things that rigorous thermodynamics will help you understand what those solutions are going to look like, different than maybe what we're used to, which is the natural gas or the hydrocarbon side of things. When we think about the overall economics, we need to now go through different scenarios. Do we want a scenario where we have storage sites for CO2 that are very close to the hydrogen production and therefore also the CO2 production? Can we include the shipping facilities, the location and subsurface where it's going to be stored close by? And we can compare that to doing something where the hydrogen is going to be produced close to the site of utilization, and the CO2 is the one that's going to be taking the long trip back to where it's going to be stored or utilized itself. All of these types of scenarios, we now need to take into the economics, not only of the zero carbon fuels, but now moving into the next section, which is going towards the carbon dioxide capture, transportation, storage, and utilization. So for this, we can start thinking about moving into different concentration ranges. I like starting at this point in time because we look at the removal from natural or synthesis gas being very high CO2. Post-combustion capture, we're going into the range of maybe a couple mole percent, up to maybe 10 or 15%, depending on the combustion equipment being used. And then we go to direct air capture, which is a very low concentration. For each of these, there's a wide variety of technologies that can be applied, but we have to think about them in the right sense. So some of them are shown here with the absorption, cryogenic, membrane separation, chemical looping, and the adsorption side of things. But how do we decide when we should use these and where the opportunities are best? I just want to pick on some of the more focal points that I found through my journeys, one of them being the composition. Of course, you also have to consider where you're going to use this CO2 and whether it's being used for the beverage or food, and you need stain removal, odor removal type applications as well within your process, or you're going for the medical and industrial, or you're just going for storage underground, or maybe secondary or tertiary recovery situations in a reservoir. All of it requires different purity. That purity can be done by the different solutions, some of them mentioned here, and this is now looking at where CO2 concentration in the initial gas starts playing better with the process considerations and logistics of different technologies. So a lot of times I've talked to companies that say, hey, we have a boiler, we're looking at 3 to 8% CO2 composition. Could we start looking at cryogenic situations? Yes, you can, but probably you don't want to. And maybe what you need to consider is membrane separation or solvent separation, maybe not to get to your final composition that you need for your utilization or your storage, but maybe to get you partway there, where then that process starts making sense. When you think about the impact that the composition of CO2, partial pressure, can have on the economics of these processes, I really like this reference right here. It's from quite a few years ago, but it's well stated in the Global CCS Institute on how much the partial pressure of CO2 impacts costs of recovery. So when we think about partial pressure, maybe we're looking at flue gas exhausts. A lot of them will be close to atmospheric. That means that atmospheric, we're looking at these yellow lines roughly in price points. So the CO2, if you can just boost it just from leaning out the oxidant going into a burner system from 3 to 3.5%, you can actually reduce the economics of your carbon capture solution by 10%. Going from 3 to 10%, maybe it's a different type of combustion system that you require. That's maybe $500,000, but it can save up to 50% of the combustion capture cost. Maybe that's double that price. So a lot of the considerations are always what type of sources and partial pressure of CO2 are you starting with? When we're looking at what solutions we've adapted within our company, our partnerships, our investments, I just wanted to mention a couple of them here today, just to make the awareness of what's out there maturity-wise in industry. So we have the membranes that we were talking about earlier. We also have multi-phase pumps that can be used. I was mentioning before for the the methane or the hydrocarbons, pushing them away from flaring, but it can also be used for CO2 injection. We have a investment in ZEG, which is a company that does hydrogen as well as a unique way of CO2 separation for storage. And also with the post-combustion capture, we've looked at non-aqueous companies, which have advantages specific to the energy requirement of regeneration and also the amount of pressure you can get as the CO2 releases out of the system for then taking away from the the post-compression requirements. So these are just some of the mentions on what we are looking at investing in and moving towards decarbonization. I'm going to move pretty quickly here just for the means of time, but what I wanted to talk about with CCS or the CO2 side, thermodynamics, just like the hydrogen and everything else, extremely important. Start with a good foundation, understand how small amounts of impurities change the impact on how you need to pressurize this for storage and where those boundary conditions lie. Sometimes you can save a lot of money for doing a little bit of purification upstream. You don't need so much compression downstream. Understanding the energy requirements also comes from a good thermodynamic understanding, and also the storage. Where are those triple points? Where are the liquefaction? If you're going to store this and ship it, and you're going to have a specific heat loss, what do you need as a safety factor to keep it in the right phase for the transportation? At the same time, with that foundation of thermodynamics, you then, similar to the other stories of zero carbon fuels, everything else, you're going to be looking towards transporting and using equipment to store it and separate it. This is just a couple of the mentions that we've done working. Back in 2006, we were already looking at how the thermodynamics impacted how much you can compress and how much you can interstage cool different acid gas considerations. And in cases of enough H2S, you can actually remove and undersaturate the gases without, removing the dehydration plant section, you can undersaturate the gases specifically. When there's too much CO2 content, it doesn't work as well, but with even mixtures or close to even mixtures for the acid gas, you can work into these types of considerations and completely remove facilities. There's also the idea of using the equipment along with those thermodynamic understandings to help decrease the amount of energy you need. In this case, going away from just the vapor phase compression, using multi-stage and multi-phase compression, going into the liquid side. Again, lesser volumes, compression, saving energy, saving money. These types of considerations and the references below, I just wanted to share here today. So the last topic, which seemed to be the one that a lot of people are interested in here, process optimization and electrification. Some of the optimization is quite straightforward and simple, and moving back to some of the topics we've already talked about. So multi-phase pumps, instead of doing a lot of individual wells, you can take the multi-phase pumps, and instead of the separation and flaring and metering at each, you can use validated three-phase metering devices, use the three-phase pumps and push these towards bulk separation where you can get larger amounts of gas and you can start monetizing at better scaled economics. So again, going back to some of the slides that we were talking about before with the conversion or the LNG, CNG power generation. At the same time, you can also do some of the steps in increasing the partial pressure of CO2 in your exhaust gas to reduce the costs of your CO2 post-combustion capture. So this is almost the optimization in your process leading to some of those earlier solutions. At the same time, you can do energy management systems. So we can look at some of the tools that we're deploying globally, such as minimizing the utility like steam consumption within, in this case, a full-fledged refinery. We've also looked at petrochemical plants. And in these considerations, what we do is we look at all the different production or creation of steam from the different boiler systems. A lot of times there's multiple boilers and different types of fuels for each of the boilers. So whether it's cogeneration or it's just steam generation, we'll look at each of the individual sources of steam. We'll look at the types of different feeds and say, these are the associated costs. Methane, hydrogen might have a very high cost. Crushed pulverized pitch mixed with some water and stuff, really low cost. But now we're bringing into the weighting considerations of the CO2 footprint. Which one's going to create more CO2? How can we minimize the amount of steam we're generating and wasting either way? And then how do we also optimize the feeds and the performance of each of the boiler systems? And one of the things that we've seen with a lot of promise here in the Canadian region is for SAGD considerations, or the steam assisted gravity drainage operations. It's the same idea. How do you optimize that steam going into the ground? And looking at it not from a steam volume consideration, but looking at it from an energy balance consideration on what you need in the ground. The other thing that I wanted to give a shout out to, I think almost every presentation in decarbonization needs at least one slide in this area, bringing in AI. You can think of it as machine learning, neural networks, AI, whatever you want to call it. But a lot of times there is a lot of good systems that we have also invested in and have in place for our own utilization, where you can use AI to speed up the considerations of calculation, and you can bring in that digital twin environment. So if you have facilities that you're running, you want to make sure that you're staying on spec with new slugs, new feedstocks coming through, but you also want to put a weighting factor on minimizing your emissions, then these are the types of systems that can keep up with those requirements. You still need a rigorous thermodynamic model in the background or a good amount of data collected, but then you can layer on the AI, the machine learning, etc., the reduced order models, and you can use this to help optimize your process at the speed at which you need to keep up again with your facilities, especially when the capacity is smaller and those time constants are smaller time as well. When we think about some of the facilities like dehydration plants, a lot of times you might look at some of the literature and say, well, desiccant dehydration, maybe it costs more, but it has much less emission footprint than something like a glycol dehydration plant, which has the vents and the flares, the pneumatic devices. But internally in our company, we've put together ventless and flareless technology innovation, and in those cases, with all of the applications that we've put towards it with very comparable costs, we can now easily compete with the emissions that we'd be looking at from a desiccant type dehydration. These types of solutions also, when you're looking at them, there's a lot of brown fields compared to green fields. So it's always recommended that you look at retrofit kits. So not something that completely redesigns the process, but something that can be put on the slide, which is the technology that we've looked at, where you can retrofit to the thousands, in this case, tens of thousands of dehy facilities that right now are contributing to emissions across North America and the world. I also wanted to mention on power generation. With this large section of combustion and the methane slip and everything going through, there's a lot of different improvements that can be seen to reduce that methane slip. Unfortunately, it also comes at a cost. Whether it's a retrofit solution or you're doing a second generation or fifth generation for some of the engine and turbine manufacturers that I've talked to, they now have a lot of different technologies that allow you to reduce the emission footprint. And again, going back to that flaring, open flare versus incineration, it's looking at reducing the methane slip and just keeping it to CO2. Talking about new disruptive technologies, we're also looking at thermal oxidizer technology vendors that can start looking at how to combust the remaining methane slip. And of course, this is looking at extremely small BTU volumes, but the technologies are getting there and some of them are looking very exciting. And again, this is looking at the brown fields. How do you retrofit what's already out there, reducing the costs, not wanting to purchase new equipment? And the last mention on process electrification, which I'll keep quite quick, just so we have some time for Q&A, we're looking at doing types of efforts like the actuator considerations. So we're replacing the hydraulic actuators, we're adding electrification. Some of the advantages above the emission reduction is we're also removing footprint. You can imagine in offshore, the footprint is very valuable. So it also allows us to bring in footprint space, maybe for other flare elimination technologies. Whenever we do these, we always make sure that we look at the rigorous emission reduction, make sure that we are actually doing what we feel that we're doing, taking into account scope 1, scope 2, and when possible, scope 3. And with the electrification, one of the things that I want to wrap up and mention is that when we're looking at today's environment and industry, we could look at the cracking furnaces are going away from the typical furnace environments with the burners to electrification. We're looking at electrifying the reboilers, electrifying the pumps, once again, getting away of that local combustion. And what ends up happening in this graph right here of a full-blown refinery, but you can imagine any midstream, upstream type facility is you bring in eventually those renewable electric sources. You start electrifying it, you even have power storage. At that point in time, potentially some of the gas, the off gas that otherwise vented or flared gas, you're bringing that as a fuel source or a heating source. It's a really good way of utilizing it, but you're still creating the emissions. When the electrification starts coming through, and when it does, those heating sources or self-power generation opportunities are going to basically eliminate themselves. So we still need to think of those longer term solutions. And one of the things that I'll warn when we're looking at the electrification of any type of process or the power requirements, always check where's the power coming from. Is it coal powered, natural gas, renewable? And based on your baseline, you might be creating more emissions than you're saving based on the technology. So there's a lot of technology assumptions. There's a lot of renewable power assumptions to make it look good. Watch out for the marketing hype. And before we get into the QA section, I'll just quickly remind of the takeaways here. There's multiple focused efforts needed for decarbonization. You can't just use one pathway to decarbonization, although sometimes there is one best pathway to start with, especially for local regions and specific types of assets. It's a strategy to plan, measure and act on the methane side of things. Remember, the measurement will allow you to recognize the achievements that you've got through your actions. Digital simulation is a key. I kept on talking about the thermodynamics, the modeling environments. We have to understand all the nuances and the specific unique considerations of each type of process for decarbonization. And innovation and experience from oil and gas is a valuable asset. I go to a lot of different universities, Canada, US, flown across to Japan. I always tell people coming up that oil and gas has the right fundamental knowledge and learning foundation to apply towards decarbonization. So we should be the leaders in this space due to our experience and knowledge. And it's a business strategy. It's not just services and technologies. It is a business strategy that we have to start as soon as possible and see it through to when it has to be applied for the different milestones. And regulatory changes will definitely impact the speed of global action, and not only regulatory changes, but also what companies decide to bring on themselves. So with that, I'd like to thank everybody's attention. I hope it was a good session. There was a lot to cover, but I'd like to answer any questions in the time remaining. Thank you.
Awesome. Thank you, Glenn. Really appreciated that informative webinar here. Thank you very much for that. We do have one comment from one participant saying, thank you much for the presentation. They really informed it, and that thank you for your investment time in this. I really appreciate it. If anyone else has any more questions, we have time for 1 or 2 questions, so you can pop those into the question function box. Just let me know if you have any questions here, and I'll shoot them off.
Yeah, I'll try and answer as best as I can. If I don't have an answer, because there are a lot of topics that we went across here, we could always follow up through Eco Canada as a connecting point.
Awesome. So first question here. Thanks, Glenn. You showed that the majority of SLB's North America's projects seem to be CCUS related. Why is
Mhm.
that? Is it just because of its strength of SLB services, or is this where the highest demand in this industry?
Yeah, that's an excellent question, and I'd say that it is a strength that we do have. We are well connected with the operators, so we are somebody that they already trust within their assets. But I think that there is something to be said about the opportunity. When it comes to the North American Canadian market, there's a lot of good subsurface opportunities for storage. That is something that obviously we do have a strength in as well. But the other thing is that when we look at the different opportunities of where different decarbonization can be held, North America and Canada is very unique that there's a lot of CO2 combustion spread out across very wide ranges. With that CO2 spread over wide ranges, that becomes a very strong challenge, especially for techno-economics. So, it's very easy if you have one large facility creating a whole bunch of CO2, you can scale up, get the advantages of techno-economics, scale of economics. But in Canada and stuff, it's a combination of our connection points, our understanding, and again, that storage side of things, and the fact that that is one of the key requirements for a large impact on decarbonization. If you wanted to say where would we start, I'd say that methane's one, and the combustion side of things is another. So I hope I answered that question well.
Awesome, thank you. And the next question here from Laura. Everything I have read to date tells me that CCS is not yet proven anywhere economically in place, work, etc. And that one key issue is that it's unique to site, so it's not yet scalable. If that is incorrect, do you have a specific example that is in place and economic that I can learn about?
Yeah, so one of the things that I think that you can definitely read up on as a good, in my opinion, a good success story would be the Quest project that's here in Alberta for Shell. So we were involved with some of the Quest project with the control systems and stuff, some of the considerations. But that project is a really good success story on how they put together a plan, they put together the CO2, and really what it does come down to is something that you mentioned within your question is the economics. It's not economical. It is site specific and such. But with the regulations coming through, we know the CO2 tax that we're seeing, that's going to keep on going up, 80 right now, but going to 170 for specific provinces in Canada to the 2030 goals. That's something that's going to change the economics. But again, if you start today, you might not see your results in many years from now. So you're kind of betting on where things are going to go. CO2 offsets and CO2 carbon credits is another area where the economics can change, but again, it's a very undefined region of the market right now. One thing I'd say that I've heard about the carbon offsets, the carbon credit side of things, is that when you look at doing forestry and everything, it's a little bit dicey. You purchase them based on a forest. Well, the forest might get logged. Unfortunately, with the forest fires, it might burn down. Well, that's kind of a non-guaranteed. In the oil and gas industry, what we do, typically we understand really well. We're building the equipment and the facilities to last long term. It tends to be a better bet, even though it sounds a little bit convoluted, that we would be going for those carbon credits from from an insurance point of view for longevity of those types of solutions. The other thing that I mentioned with locations is there's a lot of offshore and there's a lot of joint ventures going on. How does it make sense? It makes sense with size. How does size make sense? A lot of different companies joint venturing together. Those are other things that maybe you'd like to read up on. But again, I think reading up on Shell's Quest project is a really good place to start for a little bit of what I call a feel-good story.
Awesome. Thank you very much, Glenn. I think that's all the time we have for questions today. There is a couple questions asking about getting recordings of this webinar, which is great. So everyone, this will be sent out to your email within 24 hours of recording of the webinar. You can also reach out to events@eco.ca if you can't, for some reason, get it in your inbox or if there's a glitch or anything like that. So please reach out to us at events@eco.ca. And as well, too, we have 2 more webinars in this topic, so they're coming up soon. So please check out the events webpage on eco.ca, and then look at the other webinars coming up as well, too. So thank you very much, Glenn. I really appreciate it, and hopefully we'll talk to
Most
you soon.
welcome. Great. Thanks
Thank
again
you.
for the time, everyone. Enjoy the rest of the day.
Thanks, everyone. Bye-bye.